Okay, hello everyone, good morning. So, next Thursday is quiz, right? Just a reminder. Okay, so I think you can prepare the notes and also I think on your notes you can put some example to help you to understand the steps within each method, at least for the higher order differential equation. Okay. But now I would like to review a little bit what we have done on last Tuesday class, and then maybe at the last 20 minutes, maybe having some practice for the previous section or previous chapter, which is the higher order. And yeah, I think we can start with the what we have last time, which is the transform of derivative. So this is the conclusion for when we have the differentials. When we have the differentials or the derivative forms. For example, if we have the n order of derivative like this one, and then we take the Laplace transform, basically we are going to have this pattern. Okay? So for example, if we have the second order, like y double prime, we can write f and p n can be equal to, if that is the second order, this will be s squared, and then this will be fs. F becomes capital F, which means we transform into another function using Laplace, and then this will be s, and then this will be f, the small f, the original f of 0, and this will be a constant, and then f prime 0, and then minus p f 0. Okay. So the example here, okay, this is example. So usually in Laplace, to calculate and compute Laplace, we need to have the boundary value. Okay? We need to have this, because if not, there are some specific constant that we are not getting, or we are not able to get, right? So we need to have this boundary value. So the difference between the previous method that we have in first order and this higher order, we can do the first order and higher order directly, and then we add some constant c, right? We can have a c, and then we have the, for example, ce with power of mx plus c2e with power of m2x, and so on and so forth, right? We can directly be arriving at that solution. But in Laplace, we need to have exactly the boundary value. If not, then we cannot solve the differential equation. So that's I think one of the main difference between the pros and the cons using Laplace. Okay? But most of the time, Laplace is typically easier because it can be directly compute the differential equation, and we can transform easily whenever we have the n order differentials. So we take Laplace of each component of the differentials, including the right side of equations, and we get this huge chunk of equations, which we are actually easily getting this equation from the pattern that we have in Laplace. Okay, so we have the s, ys, okay, and then the y0, and this capital Y means it has been transformed. Okay, it has been transformed. And while this y of 0 is our y, and then we need to put the x equals 0 inside. Okay. And then we can have some conclusion here that so the idea of Laplace is actually we have differential equation, we transform the differential equation. And by taking the differential equation into Laplace, it means that we are going to have algebra inside, which we can solve easily by algebra. Okay, so you can think like you have like y double prime plus y prime blah 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 blah. Now you can exchange those derivatives into normal or polynomial, okay? And then that will be very easy to solve, right? So when we have the polynomial and we can solve and simplify, and at the end, after we get the simplified equations, we turn back using inverse. Okay? So that's why at the previous section we discussed about inverse. So Laplace, solving algebra, and going back to the original equation using inverse. And we get the solution, okay? Our original solution. Okay? So let's try doing this transformations using Laplace and inverse Laplace by looking at this. Okay, so we have differential equations like this. So if we take Laplace of each one of this, so let's take Laplace of dy dt, or you can write y prime if you want, and then Laplace of y. And this will be 13 Laplace of sine 2t. So Laplace of y prime or dy dt is become s, and then it's become y, capital Y, which means we transform the y, and then minus y of 0, okay, and then plus, so this will be this, or maybe, okay, and then the L or Laplace of the y will be just 3, and then capital Y s, okay, and then equal 13. This will be sine 2t. It means that we are going to have a beta here 2 over the s squared plus beta squared is 4. Okay, and this will be this, and this will be this, right? Now what is our goal actually? So you need to keep in mind that whenever we transform this Laplace, after we transform each component, we need to solve this capital Y. Okay? So solve this algebraically with algebra and solve for this capital Y. So we need to have a capital Ys equals some equation. After you simplify, take the inverse, going back to yt, okay? And that will be your solution. Okay? So we solve this. So based on the information, we have the y of 0, the initial value is 6. So this will be equal to 6. So we can write s y s minus 6 plus 3 y s. This will be 26 over s squared plus 4. Okay. Now we can combine the capital Ys as s plus 3 and move out the 6 to the right side. Okay. And then we are going to solve the Ys as 6 over s plus 3 and then plus 26 over s plus 3 and s squared plus 4. And if you feel that you want to combine both of this, then we can do that. We can combine by this denominator. Uh, 6s squared, right? Plus 24 plus 26 is 50. Right? Well, you can do at least two ways. I prefer to combine first and then partial fraction later. Or you can partial fraction this and then combine this s plus 3 with this. This is the same. But I would like to just combine and then separate the fractions. So we can so most of the time we are going to use partial fractions. So I hope you review partial fractions most of the time. When we do this Laplace, there are a lot of partial fractions. Okay? So this will be taken as this. So this is linear, this is quadratic, and we know that this is the irreducible quadratic factors, if you remember partial fractions. So this should be a constant and this should be a linear equation, right? So we add a constant on the top, a and b s plus c. So okay, our variable is s. And then let's put on the side, we can try to build up the partial fractions. So write this all together. bs plus c multiply with s plus 3 is equal 6s squared plus 50. Okay, we can let the s equal negative 3. So we exchange s with negative 3. So that will be 13a and 0, and then equal to 3, 9, 54, so 104, right? So a is what? 8, right? So a is 8. And then I think we can exchange all this. bs squared plus cs plus 3bs, right? Plus 3c. And then s squared, or maybe let me write here, s squared, maybe getting space a little bit over there. So s squared is a plus b plus s is what, 3b plus c plus 3c plus 4a, right? Or 4a plus 3c. Okay, so we get this, and we need to equal to the 6s squared, the s squared. So a plus b is 6, and then 3b plus c is 0. So since a is 8, so b is negative 2. And since b negative 2, c is 6. Okay, so we get everything. So we can write here 8 over s plus 3, and then plus 6 minus 2s. Okay. Now this is the capital YS. Okay. So at least we get 2/3. Okay, 2/3. Now another third, 1/3 is we need to inverse. Okay. So now our solution is 8 Laplace inverse of the 1 over s plus 3 and plus we can maybe let me make it space here. We can separate again the 6, so this will be 6 over s squared plus 4 minus 2s s squared plus 4, right? So we can take that as our fraction. So plus, now this we can write this as 3 Laplace inverse of, this will be 2 s squared plus 4 and minus 2 Laplace inverse of s squared plus 4. Okay, and then finally take Laplace, 1 over s plus 3 is going to be exponent, right? So a, e, but it will be negative 3, right? And plus 3, this will be beta over s squared, beta squared, right? So it will be sine 2t. And the other one will be the s over s squared plus beta, or beta squared is the cosine. So we get exactly the solution. Why? So a little bit long, I guess. But it's actually like works for all the initial value for most of the nth order differential equations, as long as we know how to Laplace transform the differentials, y double prime, y triple prime. And I don't think I will set up a question that has many orders. So probably 2 or 3 is like already high enough to solve. Because after you transform, you still have some algebra that need to be solved, right? And most of the time, you need partial fractions most of the time. So I think aside from understand what is Laplace transform and how to inverse it, you need to also practice the partial fractions. Because I believe like I think 90% you need the partial fraction to solve. So basically that is Laplace transform and how to solve a differential equation using Laplace transform. Okay? The other section after this is some property that might be useful in Laplace transform. That I think that will be next week discussion. So I think the next one I just give you some example and maybe not quite solving it. But hopefully you can try it later. Okay, now look at this. Maybe you can think and we can discuss this later with more questions to follow. This is, I think, an example question from the textbook. Okay, you can, if you have the textbook, you can look at the second example. But after this, maybe we can have more examples as well. And to end the course today, I would like just to practice with the previous sections to prepare your quiz. Okay, so let's put aside this Laplace first, and then we can move to, let me go back to, I hope you can check all this example here. This is example for, some of them are variation of parameters. Okay, you can check. I think I have I uploaded the notes or yeah, right. This one you can check. Okay, But I would like to give you more example on the Cauchy-Euler. So let's start. So aside from this example that you can try, I would like to start with, I forgot to prepare the question here. Let me write the questions, okay? So solve dE. Maybe the first one is this one first. Okay. Or maybe, hold on. Sorry. Maybe just give you the initial value, okay? Give you the I think it's okay. Just I will rewrite again. Maybe later I will give you. So later I will put some other examples below this, maybe some numbers that you can try just to prepare some practice. Okay. But for now, let's try from this one. I'm not sure whether we have. I think we have time at least 2 examples. I think. And then you should know, like, if I give you this without any context, how to solve it using like certain method, which means that you can try with like several methods that can be done. Because I think if you see like the x and y simultaneously within each component, then you need to like perhaps you need to be aware of that. Perhaps this is the Cauchy-Euler. Right? Because if not, when you try to find the homogeneous solution, you are going to divide this with the x squared, right? If you want to make it into the homogeneous. But the middle part will be 1 over x, y prime. Right? Well, if we cannot use that to find the homogeneous solution, right? The constant coefficient, if you remember. But for example, if I write the question without the x, like this one, I think we can use the constant coefficient. Like we can turn it into m, right? M squared minus m plus 1, right? And then we can propose the solution that is y equal e with power of m1x or m2x, how many m we have, repeated units or maybe a complex. Okay, that is the condition. But if we have this, then we can set up the Cauchy-Euler with our proposed solution are the x with power of m, right? So we can write that using the Cauchy-Euler. If you remember the Cauchy-Euler, we take, so this is A, B, and C. Now Cauchy-Euler is taking the plus B minus A, M, plus C, M, right? So at the end we have A is 1, so M squared. B minus A, so negative 1, so negative 2, right? And then plus 1. And then equaling to 0 to find the homogeneous solution, right? So this is the auxiliary equation. So we can factor this. And we know that the M will be equal to 1. Or M1 equal M2 equal 1. So we have a repeated factors, right? So when we have repeated factors in Cauchy-Euler, then our solution is become C1x, okay, plus the second one we need to multiply with ln, okay. Automatically we just multiply with ln, okay. So we have this two. Now based on this proposed solution on the homogeneous one, then to find how to solve this method, so suppose or let y1 is x and y2 is x ln x. We can definitely go directly to variation of parameters. So finding the Wronski the Wronskian determinants. Okay? I don't think undetermined coefficient will work like flawlessly, but the variation of parameters will work for most of the differentials. So we can just go and try the variation of parameters using y1 is x and y2 is x ln x. So we can try to using that Wronskian. So take the Wronskian and taking the x and x ln x as our y1 and y2. So this will be x ln x, and derive, okay, first derivative, and this will be what this will be x1 plus 1 ln x, right? X1 over x1, oh yeah, and this will be x plus x ln x minus x ln x. We can cancel that, and this will be just x. Okay. So our Wronskian, the result is x. And then what's next? In variation of parameters. So let me write here to give you the notes that this is using variation of parameters. Okay. Okay. Now next, after we get this Wronskian, our idea, the big idea of variation of parameters, is finding the u. Okay. So actually, the particular solution in variation of parameters, okay, we need to find u1 y1 plus u2 y2. Okay, this is the big idea. We need to find u1 and u2. That when we plug in, it will work within our differentials. And how to find this u1 and u2 is based on the Wronskian. So we are going to use in matrix we call the Cramer's rule. If you remember the Cramer's rule. How Cramer's rule works is basically we are going to exchange the column. Okay? We are going to exchange the column. So taking the f of x is equal to 2x, or now we need to stabilize this formula by taking the, let me write that the y double prime minus 1 over x y prime plus y over x squared. This will be 2 over x. So we need to make the variation of parameters in a standard form, because standard form. Okay. So this will be the f of x. Okay. So this will be using 2 over x and then x ln x, right? So this will be 2 over x. This will be the same. And this will be negative. Am I correct or no? Oh wait. This will be 0, 0. ym. Okay, so this will be 0 and 2 over x. Okay. I think this will be misleading. I think just write y double. Supposed to be 0 f of x. Okay, so this will be taking over there, and then solve the equations. This will be 2 ln x, so 0 minus 2 over x ln x, right? So minus 2 ln x. The same with the w2. This will be x, 1, and then 0, 2 over x. So 2, this is 2. Okay. And then u1 prime is this. This will be 2 ln x over x. And u2 prime is this. This will be 2 over x. Okay, and then what's next? We still have to integrate this, so there's a lot. Although this question is like quite simple, but there's like at least like three, like the first one, finding the homogeneous. The second one, using the non-homogeneous method. And then inside the non-homogeneous method, maybe there will be several steps, okay? So now, taking this u1 prime, so u1 is differentiate or the integrations of this dx, and then u2 is integrating the 2 over x dx. I think the u2 is easy to find. This will be 2 ln x, right? And how about this one? How to check? I think we can let u is what? If we have ln x, this will be du 1 over x dx, right? I think the x is x du. So we get -2 ln or u, right? U du. This will be -2 over 2 u squared, or negative ln x squared, right? Okay. Okay, forgive me my rough calculation here. Just using substitution, I think we can get. So u1 is negative ln x and then squared. So total solution is yc plus yp, right? So y is c1x plus c2x ln x plus y1 u1. So y1 is x. So this will be x multiplied with the u1. It will be negative, right? Negative x, and then ln x squared, and then plus x x ln x, 2 ln x. So plus 2x ln x squared, or we can simplify it again. I think this will be plus x ln x squared, okay, when x should be greater than 0. Okay, so I know like how much time I needed for calculation, so I think, yeah, maybe quiz only 3 questions. At least for each method, they undetermined, or maybe just undetermined and Cauchy-Euler. Maybe just 2 questions. I think enough. I think just 2 questions. If 3 questions, maybe 1 question only asking the statement and maybe true, false then. Okay. Okay, I will give you more examples, like in practice here. But I would like to know, like, how you are going to take on the questions. Oh, sorry. I would like to give you some feedback questions. So, but before that, any questions for this one? I think as long as you are consistently following the procedures one by one, it's supposed to be okay. I think the difference will be in the process. Sometimes maybe you had some problem with the algebra, or maybe you had a problem with the integral, like these integrations. But usually the integrations generally can be solved using either substitutions or the integration by parts. I think most of the case you can solve by those two methods. Sometimes you need to have some good knowledge on integration, especially for special integration, like integration of the tangent x or integration of the secant x, that need to be usually we need to, like, if you don't remember, then you need to find how to get to there, okay? How to get to the result. But I would like to prepare something that is focused more on the procedures part rather than the computations in that we learned before in calculus. Okay, I think we can move to different